Thanks, Andrew. Okay, we can get going. Final presentation of this session. Again, we're happy to have our next speaker, Mark Coates, who is a professor at McGill University in Montreal. Mark's research interests are in communication and sensor networks, statistical signal processing, Bayesian and Monte Carlo inference, with a lot of very influential contributions over the years in internet tomography. Actually, I still use some of his work in case studies I present on tomographic topology inference in my class. I think I taught this a couple of weeks ago. Anyways, also a lot of work in distributed particle filtering and learning on graphs, which I guess is going to be mostly a subject of his talk today, which I believe intersects quite a bit with Yorgos' recent work. So, Mark, thank you very much.
Good morning. It's a great pleasure to be here, both to attend the workshop and to celebrate the achievements and contributions of Yorgos. Yesterday was the 10th anniversary of the passing of my PhD supervisor, Bill Fitzgerald. Maybe some of you remember him. He was a bit more active in the Bayesian analysis community. But it did make me reflect on the nature of mentorship. And certainly Bill was an absolutely fantastic supervisor. I learned so much from him, and he influenced my life and I think my career, the way I think about problems. And in turn, of course, he's influenced the students that I've had over the past 20 years. And in our community, there's some professors who are really absolutely outstanding mentors and who just have an influence that spreads far and wide, and you see it through the number of students who go on to contribute and the way they comport themselves. And Yorgos is certainly in that small group of people who's just had a truly magnificent mentorship history. And the way mentorship goes about happening, of course, there's technical guidance in terms of how we teach the students and about the technical matters, but I think it goes much beyond that, and there are more important things, particularly the sheer infectious enthusiasm for learning, the rigorous thinking about problems, and just the examples of Yorgos behaving that way and students being able to perceive that's the way I should act. That's what real mentorship is about. And I think we'll see today, just with the number of students who'll pay tributes to Yorgos, that really it's been a fantastic achievement over the past 20-odd years. I first met Yorgos, I think, good 20 years ago when I was just starting my career. And those are the days of network tomography that I was working on. I think we intersected there with network monitoring. From there, I think the next major interaction was consensus algorithms, and certainly Yorgos influenced me in many ways. I could talk about lots of research contributions in those two areas that shaped my thinking about those two topics. More recently, it's been perhaps this topic, learning on graphs. How do we take data that is representing relationships between entities and dependencies and make the maximum use of that information that we have, both the interrelationships and the actual data at the nodes. And there Yorgos has made many contributions and has certainly influenced what I'm going to talk about here. One of the benefits of being at McGill, so McGill's a great place, and I'd encourage you all to visit and come to Montreal. Montreal's a fantastic city. But aside from that, Montreal and McGill has a really nice possession that was donated to it many, many years ago as a research facility at Barbados, right on the coast, the west coast of Barbados. And I run a research workshop there just about every year. Small group of 20 people, we stay for about a week. It's a great workshop because we have a very intensive interaction for a week. And Yorgos is really a person who exemplifies the work hard, play hard side of things. And so he's been a regular attendee at this workshop for the past decade, roughly, I think, off and on. And in those chats that we've had many chats there, sipping a quiet rum on the beach or in the workshop as well. He's presented ideas that have shaped this particular topic, thinking about this. And we'd ask why graphs? Well, there are many, many examples of where graph learning can be useful, and these are topics that I've worked on. So communication networks, the graph is obvious. There's a graphs of interactions of communication. Sensor networks, we clearly have another graph. But then there's some cases where the graph is there's no physical graph present, but there's certainly something that you can use, the interactions, and a recommender system would be an example of that. We don't have any sort of physical interactions, but you can represent the interactions, the clicking of items that a user might do, that there's a graph structure there. If we look in the bottom right-hand corner, there's circuit design, and so circuits, again, we can represent this in a graph and do things like inference of potential congestion when we do the circuit design process. Up the very top, we have knowledge graphs. Knowledge graphs and reasoning graphs are starting to exert even more of an influence as we start to think about foundational models and large language models, and how can we use knowledge graphs and reasoning graphs to better shape the answers that we get from those types of models. So lots and lots of problems of where we'd use graphs and we have interactions and we'd like to make use of them. But then, of course, there's an issue. In many cases, these graphs aren't real graphs that get presented to us as ground truth. This is the exact graph that you should be building on. It's usually an uncertain observation process. So you have a presentation of a noisy graph, or there's been a model that has been used, an algorithm that's been used to derive a graph that you're presented with. So there's uncertainty. There's spurious links. There's missing links. If you think about going back to the recommender system example, we have the case where, well, I might be interested, a few years ago I was interested in children's movies, not as a pure interest in myself, that would be a bit disturbing, but I had young children, so I'd be clicking and searching on a lot of children's movies. There'd be a few that we watched, and that would be the ones that I interacted with. But then there's a whole spectrum of movies that I didn't interact with, but it could have been potential interests. And so the true graph there is my potential interests, all of the interests that I would be if you presented this to me. Yes, that's a good movie, I'd like to watch that. And so that's the graph that we'd like to process and use when we actually have a very sparse graph of what the actual interactions were. So there's a question there of how do we go about taking this noisy graph. And the first thing I'll talk about actually is what happens if there's no graph at all. What do we do then? But we know there's a set of relationships that we could exploit and we'd like to exploit. What do we do in that circumstance? And that gets us to this topic of topology identification. And this is one area that we did talk about, I think, about 6 or 7 years ago at the Barbados workshop. And Yorgos introduced some of these ideas or some summaries of those ideas and suggested to me. And it's a very elegant approach. So this succession of papers about topology identification for learning over graphs, various approaches for doing it. And I think one of the most elegant approaches is this notion of structural equation models. And then structural equation models are very nice for representing, say, the linear relationships. But of course, in many of these graph settings, you'd like to go beyond that to nonlinear relationships, and there the kernels get introduced to handle the nonlinearities. So the rough idea of Yorgos and his collaborators in terms of this structural equation, or the structural vector order regression approaches, to have a model where if you observe time series at each one of these nodes in a graph, you can pose that there's a relationship, causal in a sense, such that in these nodal time series there are dependencies from one node to another. They could be instantaneous. We've got the blue lines here saying at this particular time instant there's a direct interaction between two nodes, or they could be historical in the past relationships. And so what we're interested in doing then is taking a look at this problem and posing it as an inference problem where we have a collection of nodal time series. We introduce the kernel matrices to handle the nonlinearity aspect. We have the collected alpha coefficients, those relationships that we just saw in the structural equations, and then some regularization terms to standard things. The nice thing about this problem that Yorgos and his collaborators posed is it's a convex problem, and there's a very nice and fast ADMM inference procedure in order to solve this and get yourself a graph to start working with. I talked about the influence of my supervisor. I was indoctrinated, maybe too hard a word, but the Cambridge lab was very Bayesian. Bayesian this, Bayesian that, Bayesian this. So I often think about problems in a Bayesian way. A slightly different way to approach this problem is to think about it as a Bayesian inference problem. And now we'll get back to the place where we have a partially observed graph. We observe some of the graph, and we will introduce a prior. We'd like not to impose too strict modeling assumptions on this, so we're going to, I've said non-parametric, maybe semi-parametric is a little bit a better word, but we're going to keep it as simple as possible in terms of this graph model that we'll introduce. So just a term to avoid isolated nodes. We prefer not to have any isolated nodes, or as few as possible. A term to encourage low weights. We'd like some sparsity in the graph, and just some constraints to make it positive and symmetric. We'll think about undirected graphs here. And then a likelihood expression that we need to complete the Bayes framework. So this is just expressing that we have an exponential relationship, and what we're trying to say is that neighboring nodes should be like one another, similar to one another. We can capture that by saying, if I form an embedding of these nodes, I can use graph neural networks that we heard about before, or a graph structural embedding, whatever I happen to choose. Their embeddings, the distance between the embeddings should be small if those graphs are connected. Similarly, if I have labels associated, I have access to labels associated with nodes, I'd expect neighboring nodes to, in general, have similar labels. So I can form a likelihood function like this, where I haven't imposed too much modeling assumptions about the graph here. I've just said, let's try to keep it connected, let's try to keep it relatively sparse, let's keep the weights reasonably low, and let's obey what we've observed and have embedding distances close to one another. So this is an example of a citation network. You can see on the left, from where you're sitting, it might just look solid blue, but there are some little dots there. It's clearly a very sparse network. Most of the graphs we work with are extremely sparse. And if you try to do inference leveraging the connections on the left, well, you're not getting much bang for your buck, right? There's too few interactions to really get better inference happening. If we apply this inference procedure, we could go down the structural SEM route. We could do this as the semi-parametric Bayes route. We get a much richer graph intercorrection structure. We're seeing that the block structure is emerging to say these are fields that are close to one another, that are citing each other quite regularly. And now when we use this dependency to do our inferences of particular labels of these nodes, then we'd see a much improved performance in terms of the gains we can get. So the ones on the right here are where we've used some inference techniques building upon the graph that we've inferred. Now, this is nice in a tiny little citation network. We're not very interested or enthusiastic. Who cares about citation networks? In fact, I think that's something I say to my students most often. Stop analyzing these stupid citation networks. I don't want to see them ever again. But these algorithms do have use in practical settings. And so this is an example of a recommender system, an app recommender system, more than 500 million users associated with this, more than 200,000 apps. And if you use this type of inference procedure within that embedding system, we had an online A/B test for 10 days where you're inferring the graph and making recommendations according to that, building it into a graph-based recommender system. Then we saw that on average a 10% improvement in terms of the click-through rate. So because we're getting more diverse recommendations, we're exploiting this use and exposing much more interesting things to the users as they'll click through with more probability. Okay, I think I'm getting relatively tight on time, so the second half of this talk is going to be very brief, much briefer than I perhaps planned. But it's harking back to my signal processing background, and what I wanted to talk about briefly is maybe a slight tension between attention. Transformers are everywhere. I've started in signal processing and perhaps maybe a little bit more in the machine learning community nowadays. So transformers is a predominant approach. And then we have the convolution. We heard about graph convolution earlier today. And so there's a bit of a tension in the graph learning community. Which one of these is better? And I think the big question is, do we really need attention? Is attention necessary? Is it really bringing something important? And if I think about attention, well, from a signal processing perspective, I think this is just we can rethink about it as this is a filter. It's still a convolution process, except now we have convolution weights, filter weights, that are dependent on the actual signal, right? So that's where we go from attention. In the convolution setting, the filter weights won't be dependent on the actual signal at the nodes. And so the question is, does that dependency on the signals at the nodes really is a critical factor in terms of our learning capability? So this is just a quick, we'll skip over this slide, but it's a quick indication that most of the standard graph convolution approaches, fixed coefficients, can be implemented using a message passing neural network. Message passing neural networks have some issues, some problems. One is over smoothing. As you run the filter over multiple layers, so depth in neural networks is important. If I do many, many layers of convolution, standard graph convolution, I get this smoothing phenomenon that's not great. I have over squashing phenomenons. This is buttersnakes and gumballs. It's an Australian children's story. They squeeze and shove them into tin cans. So this is a phenomenon we're trying to get across a graph. If we have bottlenecks in the graph, it's hard to get that information across the graph using a convolution approach with multiple layers. And finally, there's limited expressive power. So if we think about the Weisweiler-Lehmann test, we can demonstrate that the ability of convolution to distinguish between graphs is relatively limited. WL1, the best algorithms could do WL3. All right, so transformers can solve these problems to some degree. And to keep the story short, if we use a good way of encoding the position of the nodes, so a very powerful way of using the position of each node. The one that we've proposed is random walk and powers of random walks. So if we collect powers of random walks, and this encodes where is a node in this graph, then using that positional encoding within a transformer architecture, we can get much more expressive WO3, so higher order expressivity, and also just in terms of performance, this will be the state-of-the-art performance, better than all other procedures. What's the disadvantage of this? So I said, okay, transformers are best, graph transformers are best. Big disadvantage, well, they're complex too. So computational complexity is a disadvantage, but beyond that, you need to stick in softmax layers in order to make the learning converge. What does softmax do? Well, it says those filters all have to be positive in their coefficients. And suddenly we're at a point where can we learn filters that are doing high-pass actions, which we'd like in signal processing? No, we struggle with transformers. So transformers good on one side, give the best empirical performance that we've found, but they have this nasty property of strictly positive filters and computational complexity. So rethinking that, recent work is, can we go back to the convolution setting, do with fixed filters? And the short answer is yes, if we use this powerful positional encoding and then switch into a regime where we're doing continuous kernels, building our kernels using passing it through a neural network based on this positional coding as an input. So we have now coefficients that aren't dependent on the signals, but they are dependent on the positional encoding that we have for the nodes. Then we can get back to the performance and the expressivity of the graph transformers. And what's interesting is that we do learn high-pass structure filters, so filters that have positive and negative coefficients. And by forming ensembles, we can see that the transformers and these convolution filters are learning different things. They can work together, and that's maybe the future step is how do we optimally combine the strengths of both these architectures to get even more powerful graph learning mechanisms. I'll close it there, and happy to take any questions.
I have one. I was going to ask, let's say, just prior to your first slide, I was wondering, let's say, there's dispositional encoders, there's the transformer in a way. I was going to say, where is the power coming from? Is it both or just, and then it seems like the transformer not necessarily. And what kind of, is there any improvement or what's unique to dispositional encoders with the random walks? Could there be anything else, let's say, to extract more juice from there, or do you think there's not more room for that?
I think there's definitely room for exploring what would, so the question just to, I think, in case anyone didn't hear it, was what is giving the power to the transformers? Is it just the positional encoding, or is it the capability to have dynamic weights? And the second part of the question, is there more juice to have out of different types of positional encoding? I think the answer to the first question is strength is coming from both capabilities. So the fact that we were able to take powerful positional encoding and use it in a convolution architecture and get almost the same performance as the transformer shows that there's a lot of juice coming from the positional encoding framework for a transformer. On the other hand, when you use them together, you do better than just using convolution filters alone or using transformers alone. And that suggests the dynamic weights are playing a role and can be used in a complementary fashion. In terms of, is there juice to be had from a better positional encoding? Well, I think yes. We definitely haven't proved that this is the absolute best. We've shown that using the random walk approach, you can have close to as expressive as any graph neural network that we know. It's sort of just about the best that we know. But that's certainly still, there are question marks that we should still be able to go beyond that in terms of expressivity, and I think there's research to be done on better positional encoding mechanisms, and certainly less large ones. The random walk with many powers starts to be a very memory-hungry representation for a graph.